March 30, 2023. According to the solar-powered sundial here, solar radiation is almost enough to get the solar-powered executive desk toy spinning. Today I thought I'd read from Hermann Weyl's The Continuum, a critical examination of the foundation of analysis. And Hermann Weyl is a famous guy who, after the era of Einstein's Annus Mirabilis, 1905, sometime later, the development after the quantum effect, because experiment and theory was showing that light and electrons are both wave and particle, milk and oil drop experiment, and some of these other things that led to the initial development of the quantum theory and atomism in the area of the 20s, the 30s, and this time where we have the significant contributions of Pauli and Dirac and a while later, who would we speak to? Born, and then Bohm de Broglie. These days, Bohm and de Broglie's models of the effects of quantum interactions have come back. For a long time after what was called the Copenhagen Conference, where the quantum theorists of the day met and decided to discuss how they were going to make interpretations of quantum theory. There was what resulted that it was after the statistical hypothesis that basically quantum mechanics observe and obey as if they are random. And thus that then when we get into what happens with after the dual slit experiment and interference, and that these waves, though at random, happen to exist in the regimes, and otherwise the spooky behavior of quantum particles, and that the upsampling, measurement, and observer actions have effects. That in this era, then it came up a lot of the initial notions after Copenhagen, the conventions of the description of the quantum numbers as what reflect then for our measurement of the atom after the measurement of the electron of a particular size of an atom, according to its atomic number, which has been so established, like after Lavoisier or something like that, that then there was otherwise what became of trying to deal with what is at once a discrete phenomenon, the particle, that quantum mechanics is a theory of particles, that they live in a field, and as they propagate as waves, rays and waves, these particles. So the discrete vis-a-vis the continuous has always been a defining feature of why quantum mechanics is as of a discrete theory. Thus that all our lessons of the classical from mechanics and kinematics kind of add into our billiard ball model as of what was along the lines of Dalton, or the pudding model, or Rutherford. Let's not forget Rutherford and these sorts of inputs to what became the early notions of the quantum theory for the atomic theory. There were then various experiments that basically established that quantum theory was a thing and only explained in its milieu, in this regime, which is, of course, the microscopic. Essentially always beneath the visible of what's the quantum, in terms of the flow and the ebb, and then we will differentiate flow and flux, where flow is as a fluid model and flux is as of a light-like model, ethereal or as a gas. That various notions of besides various notions like the Dirac positronic sea, which basically establishes that space is full of a constant state of symmetry between particles and virtual antiparticles, the positrons. That when we say virtual, we kind of mean hypothetical and only mathematical, yet at the same time in these fields, they represent the flow the other way. We're never ever actually experiencing what are points in discrete objects in this particle theory, but that is an aggregate of them. It's a flow of them. It's a current of them. They have a density in their areas and volumes. vis-a-vis that when we talk about a test particle and this kind of stuff, it is like so. There was then up to Schrödinger after Heisenberg, where Heisenberg basically established the uncertainty principle. You can't know both the position and momentum of a particle. It has a position and a momentum, but what it reflects is that according to the sampling, measurement, and observer effects, that there's always introduced that the more precise is determined one way, the less possible or more unsure or uncertain it is the other way. Yet it is still so that things travel through a medium according to their ideas, and the idea that if you have a perfect synchronized timekeeping apparatus, that the emission of a photon and the arrival of a photon perfectly determine both its momentum and position, that there is yet with regards to why there isn't Heisenberg uncertainty principle, that it's a matter of effect, that it's a matter of devices, it's a matter of the regimes and what results to have such a precise machine that the detector is able to make something that detects a particle and that measures as it samples, as it's observed, the energy of the system and the transition of the energy that must have been some effect that drove the detector. That then for Schrödinger is his deliberations on the superposition of states, and why when we talk about the superposition of states to reflect our otherwise probabilistic nature of events, and that then the measurement, detection, observer effects results that there's a superfluid sort of model or superflux. And this is along the lines of whether Bowman-de Broglie's wave equation, the Schrödinger wave equation, which determines for a particular contrived simple system its quantities as quantum properties and its quantities as classical properties, that then Schrödinger's, including one of the most famous thought experiments of all time, Schrödinger's cat, that exists in a superposition of states till such time it's observed, sampled, measured, what is the outcome of his predicament, that this as well reflects what are conceits about the limits of the model, the particle model in the probabilistic setting. What as well reflects that in these higher order wave mechanics, in the nonlinear as we've been discussing, that the theory of potentials results how this superwave works, that when we talk about things like that gravity's speed according to Newton is no less than infinite, or that the geodesy according to general relativity is always instantaneously evaluated everywhere in the same milieu, where light's speed reflects a limit to the flux of light in a vacuum, and that according to the kinetic energy that it's usually talked about in its normal natural units, when in the sense that it's equal to 1, it's equal to infinity, vis-a-vis 3.00 or 2.98 times 10 to the 6th or 8th, I forget, meters per second, where the electrons move about 10 to the 6th and photons move about 10 to the 8th meters per second in a vacuum, or a perfect conductor, irrespectively. So I thought I'd read some from Hermann Weyl's The Continuum, a critical examine of the foundation of analysis, because real analysis then is on the mathematics side. And the notion of the paradoxes of Zeno, the thought experiments of Zeno, or Gedanken, is something that's kind of that we're thinking about or we're thankful for, is the word from German for the thought experiment. Those of Zeno are variously famous as Achilles and the tortoise. The tortoise and Achilles engage in a foot race. The tortoise has a head start. So every step or forward motion that Achilles takes, it catches up to the tortoise. Yet, at each step, the tortoise moves forward also. So the paradox, or how it must be resolved, is when does Achilles catch up to the tortoise? And then we talk about that variously in terms of straight tracks or circular tracks. And other examples of Zeno's contemplations on the notions of continuous uniform motion in time, and whether or not time is considered a continuous quantity, where here it is, as according with a clock hypothesis. There's that, for example, the arrow of Zeno is something that an archer shoots an arrow to a target that's at a fixed distance away. It travels half the way there, and then half of that again, then half of that again ad infinitum. There's that adds up to 1. And that whether it does or doesn't makes for, of course, that in our curriculum, we learn instead that we talk about that in terms of limits, because trying to establish it in terms of arithmetic would introduce infinite and correspondingly infinitesimal quantities into what are otherwise are real and rational quantities, as all follow from the unit, as all follow from the mathematics of the time called geometry, which is a very particular and central and relevant notion that sits along with real analysis, where Hardy, in his book Pure Mathematics for us, equates what are the points of a line of geometry and the real numbers of the real number system and these things. So the foundations of analysis for real analysis in mathematics are, of course, totally central and critical for all matters of physics in their treatment of what would be continuous quantities, or in any sense where there's something like time that's infinitely divisible or not. And of course, it corresponds with the way physics is, that these are not tractable in many particular senses. And so when we talk about the point and particle models of physics and what they mean in terms of the quantization of making from an impulse a linear infinitesimal impetus that results a direction or the gradient in all the field of a wave, which is, as Born put it, in a restless universe of a sort, that these kinds of things are what became, as for after Rayleigh and what's called the ultraviolet catastrophe, and when we can't really have an infinite variation of the energy in the quanta of light or the quanta of electrons or the transitions of electrons in their orbitals in our measurements in accordance with how they are and where they work in the statistical ensemble, that is statistics together of all these things, how it works. So the notions of the continuous and discrete from mathematics are entirely relevant to the notions of continuous and discrete in the physics. And so from Weyl, who's a mathematician of sorts, and his discussion of the foundation of analysis, a critical examination of there's that we have what's these days, we call it a standard real analysis. And it follows from after the course of pre-calculus, which is where we examine the setting of real numbers and discuss and establish that we can't deal reliably with infinitesimals and infinities in our usual arithmetic. There's instead the derivation via usually a system of proofs and derivations called delta-epsilonics. And these provide for us what's called the notion of the limit. And delta and epsilonics is named for that two variables are named delta, which is a regular also word meaning change, the change or delta in something, is then phrased in terms of a smaller quantity called epsilon. That between delta and 0, there's always an epsilon. So by following some simple concepts, that it's direct and linear in the curriculum to have delta epsilonics make for proofs that what is so holds for what would otherwise be the infinitesimal analysis, which is what it was called for hundreds of years, though often found lacking because of this lack of rigor. Its critical foundation, its formalization that's so suited that it does not admit any ambiguity or otherwise room for error, as it were. That delta-epsilonics is the instructional method and the setting of our proofs and derivations of the theorem of the existence of limits. And then this is gets into then what's called the intermediate value theorem, that by demonstrating the intermediate value theorem, then there's demonstrated the fundamental theorems of the calculus. There's the fundamental theorem of the differential calculus, which is computing the rate of change of something with respect to something else, and the fundamental theorem of the integral calculus, which is the mensuration, the computation of the area of quantities over quantities. The inner and outer products of a sort, if you will, or as recalled from a previous discussion. So in the course of standard real analysis, then we get into some other notions of how we define for the algebra and the arithmetic what are the settings from after some set theory. There's established what is called an algebra and the operators of addition and multiplication for the arithmetic of integers, that's a thing. And then there's built what's called the ordered field, and the ordered field is the field of rationals, that all the ratios of integers, all of their reduced forms where there's no common factor that they share, these numbers that they're coprime in a sense, that the rationals then are all the numbers that are ratios, and they fill to the point of density all the space between the integers. Now these aren't quite continuous or gapless, complete in the sense of continuity, because it's shown there exist irrational numbers, irrational numbers. Now the irrational number, the most familiar example usually is square root of 2. And there are a variety of proofs that given a right triangle with sides 1 and 1, the sides next to the right angle, that the hypotenuse has length root 2. And these irrational numbers are what's called algebraic, because if they're the roots of a polynomial equation, they are not necessarily rational numbers, but they are yet algebraic numbers. So these numbers are also dense in the real numbers, and in each other, that between any two rational numbers in the field, there's another rational number, and in between any two algebraic numbers in the field, there's another algebraic number. And ditto, that between any two algebraic numbers, there's irrationals and algebraic numbers. Thus, that beyond the algebraic numbers, everything else is what's called transcendental. So there are the integers, there are all the fractions of those, each one together establishing the modularity under the integers, and then all those put together are called the complete ordered field, or the ordered field rather. That the completeness, what so follows, is that after the algebraics, which is yet a field, I imagine, if I don't recall incorrectly, that there's the complete order field, which includes all the rest. And then we might wonder if there are transcendental numbers, how we can provide an example of one. And so the usual most familiar examples of transcendental numbers are pi, the ratio of diameter to the circumference of a circle, or e, the natural logarithm, and that it's long been proved that one or the other of those is transcendental, and that they are both so. And then, and this besides that there are ratios in numerical coincidence that get very, very, very close to pi, like 22/7, and other terms that have small numbers that are accurate when you evaluate them to be many, many, many of the first digits of pi. So as with regards to the constant of the natural logarithm, as well, besides, for example, a numerical coincidence, as we call it, something like pi has a lot of very close approximations, there is that there are many different ways to write expressions that evaluate to e, 2.728 or dot dot dot, which basically finds one of its most usual settings in the computation of an interest over time given continuous compounding as per the principle of compound interest or growth. And there's also the infinite sum of, you add 1 plus 1 over x, and you take the infinite product out on that, and it results e. It represents also its finding in many of the geometric shapes that result naturally according to natural processes of growth. And it's similar in that sense to where we find the algebraic mean, which is where root 5 over 2 represents a particular harmonious quantity that's under the algebraics. Yet when you line up basically root 2 and then 1 over root 2 and then root 3 over 2, that gives most of the usual segments as per trigonometry, the values of sine and cosine according to Pythagoras and trigonometry. And then there's also that there's a geometric golden mean, root 5, about root 5. And then there's pi in related quantities and pi squared, and pi in terms of higher order spheres. And then there's e, the natural logarithm. And then there are a variety of other well-known or usual constants. There's zeta and eta, and there's Apries constants, and these are generally transcendental and arise as the constants relating progression in numerical constants, and these sorts of things. These are Euler-Mascheroni constant and this kind of thing. So all these together, once you have the integers which form a lattice and the real numbers which form both a clock arithmetic like an Aristotle's continuum and a complete ordered field that's gapless like a Cauchy, or originally Eudoxus was in the ancient Greeks who framed this. That there's Aristotle and Eudoxus and then Dedekind and Cauchy and Weierstrass, for whom there is, after Cauchy and Weierstrass, that these real numbers are defined as all the sequences that arrive and have a limit in these numbers, and it's so written that you can write each one of the real numbers as an infinite sequence of digits. And it is so that in this way of writing real numbers, and there are others, that every real number that ends with b minus 1 or 0 in the given base representation, or as per the radix, that this expansion has a dual representation of numbers. That how it's built in the standard curriculum of today is that the real numbers are the equivalence classes of sequences that are Cauchy, that have the Cauchy property, that result that the limit exists for at least one sequence that, as a series, has a limit, and that would be its sum, a value as a real number. And so the usual curriculum, as was provided in abstract algebra and after the usual high school course of calculus, pre-calculus and calculus, and after a usual course of abstract algebra and real analysis, it has that. It so follows that then we have, in terms of this complete ordered field, then after the properties that are provided by the ordered field, then there's added basically two axioms. One is called the least upper bound property, that for any given set of these things, that the least upper bound of all the elements in the set does exist in the greater set of all the numbers. That's an axiom, basically, added to the definition of standard real analysis. And then there's measure 1.0, which basically says, as we get back to our definition of the metric and the metrizing and the existence of this thing and its relevance to real analysis, that's the second axiom added after otherwise what just arises from the definition of the integers as per Peano's integers, and then the definition of addition and multiplication per Peano arithmetic and Pressburger arithmetic, which variously, given their perspectives, are first and second order, or not, just first order. And that then there's the field, which is the equivalence classes of reduced fractions. And then there's the complete field, in the ordered field and complete ordered field, respectively, where the that is defined in the usual standard linear curriculum of standard real analysis as the equivalence classes of sequences that have the Cauchy property, that they have some sequence that has as a limit this value in what we call then the real numbers. Then for systems of real numbers, and now these are three different things, and so you can't really apples and oranges, 1 and 1.0 and 1 over 1. They're three different things in these three different models, and we just talk about them all together as being real valued because it results that the integers are embedded in the rationals and the rationals are embedded in the real numbers, and that thus these properties result that all of our delta-epsilonics and the intermediate value theorem, that being pretty much all you need to know to establish the fundamental theorems of calculus, that those are then rest what follows arithmetics and what are derived as the rules for differentiation and integration. And that those encompass and embody what we call the inventors or discoverers of the calculus, who we talk about Newton and Leibniz as concurrently discovering Newton's fluents and fluxions and method, and Leibniz's summation bar and the differential, which is the notation we employ today, where sometimes we'll write f prime for the first derivative with respect to and the Newton's notation. That then a bunch of other of these methods as after Leibniz, which basically treated the differential as an algebraic quantity, yet though admitted one misstep, making it very easy to introduce ambiguity and this incorrectness in this system, that's about what real analysis has been arrived at, that it's the same for everybody, it's a linear curriculum for everybody has access to the same derivations, and that in this manner, that's what we call standard, and it admits no infinities nor infinitesimals, and that its field is an Archimedean field that has finite numbers everywhere that range from negative infinity to infinity, of course, and that as about zero they are completely dense, and that there's an infinitude of these numbers in between any two numbers. So that's what we call the Archimedean field. And when we talk about Newton and Leibniz, long before that, there was what were called methods of exhaustion. And so the notion of the limit and the approximation that only so results in a perfect quantity when taken to ad infinitum is called methods of exhaustion. And this was invented long before by the ancient Greeks, and where we assigned them to schools as of about Aristotle and Eudoxus is involved in this, and then we have like Democritus with his ideas of atomism and the points of the continuum, vis-a-vis these notions of Zeno, which are the thought experiments of the quantities in continuous time and infinitesimal and infinite amounts of these quantities and their numbers. That this is a sort of snapshot of our real analysis since Greek antiquity, our real analysis since formalization in the European continent in the 17 to 1800s, and then what today is called math, and as is taught in schools. Now I'll leave it at that. That is pretty much what I'll agree is called standard real analysis, and that it's important not to leave out any of the underlying derivations to take shortcuts, which is sometimes done to make things easier or simpler or in lesser words, because then that is kind of a incomplete context. I'll just say there. So let's take a look at what Weyl has to say here. Hermann Weyl, The Continuum, a critical examination of the foundation analysis, translated by Stephen Pollard and Thomas Bowl. Any errors or mistakes are my own. 2 parts of this book were originally published elsewhere. They are an article by Hermann Weyl, Der Circulus Eudoxus and der heutigen Begründung der Analysis, published in the Jahresbericht des Deutschen Mathematiker Vereinigung, Bond 28, 1919, pages 85-92, and excerpts from John Archibald Wheeler's. Wheeler's another guy in the quantum analysis and also cosmology. Hermann Weyl and the Unity of Knowledge, published in American Scientist, volume 74, August 1986, pages 368 facing. The translators express their thanks and gratitude to the copyright holders for their permission to use the above publication. Notes to the Dover edition. Again, he comments is advice and encouragement by the translators of John Corcoran and Ignacio Angelelli. So Weyl starts in this outlay of chapters. Chapter 1, set and function. Chapter 2, the concept of number and the continuum. So set and function reflect that the late 19th century saw a guy named Gottlob Frege have this really great outlay of his foundation of a computational setting and a logical setting called the Grundgesetze of his Beweis or whatever, that is resulted that he came up with a logical framework for what today we'd probably call predicate calculus. And predicate calculus is the means of pretty much everything in terms of what's rationalized. That Gottlob Frege had put this together, and then there was the Mengenlehre became very, very central, because the set theory had been already developed by earlier people in the field, where you can define a set as just a collection of things or its elements. One way or the other, it's only one relation, and we call it ELT, for element of. And so a set is this very fundamental thing. And then we can talk about how what really resulted for analysis in this time was that Georg Cantor put forth an assembly of a variety of proofs in set theory, and as about some properties of the density of numbers and what are real numbers and what are rational numbers, that we have what are called Cantor's original proof about the MW proof. We have what's called the nested intervals, and then we have the anti-diagonal argument, and these and a couple of other ones that we call geometrically related. And then we have the in the pure set theory or framed only in set theory as a matter of quantification, there's the power set result. These establish what is a key touchstone called uncountability. This is where an infinitude of numbers is infinite. And by its very property, it's always infinite. And for example, from Hilbert's Hotel, which is a thought experiment, there's something that's infinite. You can always move something to the side and fill it up with more in the infinite. And this is, again, one of the reasons why we have this regress, that what's infinite is infinite, and thus it can't be made finite. Or that it's intractable, that it's ambiguous, that it's impossible to relate it to, back again in the essential and the classical, finite. And so the uncountability established an inequality between the size, where cardinality for finite sets is as simple as the count, it's the size. And that cardinality for infinite sets is as to how there exists a function that's one-to-one and onto between a domain and range, which are our usual notions from functions as of the elements on the left and the elements on the right, how they relate. That a function is either an injection, one-to-one, or a surjection, onto, or a bijection, one-to-one and onto. That jection is from throwing or casting. That this result in uncountability was astounding, and it really made for what results the milieu of the continuous as it relates to the real numbers. That it established this inequality between the cardinality of the real numbers and the cardinality of the integers. Its basic fundamental statement is that the integers does not have a function that's a bijection between it and the real numbers. It does to the rational numbers, it does to the algebraic numbers, but it does not to the real numbers or any other complete ordered field, where the complete ordered field is equated to what's called Cantor space, or the space of all sequences of zeros and ones, all infinitely many of them, infinitely long. That the set that's countable and countably infinite, which we relate to the integers, does not relate to the set that is the complete ordered field that relates to the power set of integers, which relates to the Cantor space. So with this established, it really was it was used in everywhere. It became what was the rule that made it possible to establish that a bunch of other sorts of the formal developments for the rigor and these things resulted why it became so outstanding as of what it means for the infinite and the finite and the infinite and the higher infinite. In terms of the ordinal arithmetic, which is of the countable, the powers of the countables are still countable, but in the cardinal arithmetic, cardinal exponentiation, the powers in the cardinal exponentiation are not thus relatively countable. All right. So this established in the transfinite, it's called the transfinite, or transfinite, the transfinite, that there is this cumulative hierarchy of all these higher order infinities that have only one relation defining them, that it's in as accords whether a function exists on them, and so that all these classes otherwise of the countably infinite and uncountably infinite can be organized in this hierarchy, and that was a big thing. Now, this didn't all just magically appear. Mathematics is discovered, not invented, and it also was a collection of various notions that developed over time. Cantor was original and novel in some of these things, and he brought them together. Thus, that when trying to adopt something so radical in this kind of sense at the time, it was possible to do that at once and kind of have one Band-Aid at a time sort of thing. Now, this doesn't necessarily reflect the same thing as Aristotle's notion of the continuum, and it doesn't necessarily reflect the notion that the continuum is just that which is not grainy or smooth, like a Nyquist-Shannon continuum, we might call it. But it does mesh very well with the complete ordered field, and delta-epsilonics particularly, where delta-epsilonics and Riemann sums is how we do standard real analysis, and this fits well with it. So when we talked about Gottlob Frege and his Grundgesetze, and so about the same time as Cantor and briefly afterwards, we have Russell. And Bertrand Russell is an Englishman, and he's a logician. And he's most famous for his theory of types after set theory. Because set theory, for it to be profound and astounding and fundamental, elementary, and that we write all the rest of our mathematics in it as a working theory for all our objects of mathematics called descriptive set theory, is that, first of all, Russell, and we'll speak of Gödel later, for Cantor, Gödel, and Russell representing the zeitgeist of the time and this school of the abstract deconstructionist side of our standard real analysis. Russell is great in a lot of senses, if not so much in some other senses. He established first that there's something called Russell's paradox. He got into the realm of the logical paradoxes which arise of the non-logical objects, or the logical objects that arise when we consider the quantification of these things as a whole. And so, for example, there came along the lines of that the set of all sets that don't contain themselves would contain itself. It's kind of like the liar paradox. This sentence is not true. It establishes by its evaluation that it causes a short circuit in the reasoning that it brings along, has a partner, or like as a Sputnik of something that it companions it, this element of the set that otherwise was by the specification not included in the specification. And so what happened first was this sunk Gottlob Frege's effort, because Frege, when he was told this, he's like, I can't fix this, and he basically bowed aside. Then when it became to we need a formalization of these axioms for these elements, kind of like Euclid's axioms, which are so famous for geometry, that we need some axioms that are independent of each other, yet so together composed to expand our comprehension by all the combinations of the existence results for all of them in our axioms, that this resulted that Ernst Zermelo and A.A. Fraenkel, that we have for them named the ZF axioms, or Zermelo-Fraenkel axioms, that these are two things. One, there are the expansion of comprehension, like there exists the union of a set. There exists a set, its elements. There are ways to comprehend for each of these sets all the theorems that are initially result is from these independent axioms, and there's about 7 axioms, and one of them is a schema, that there's separation, and that there's power set, that the power set exists. And there's a few more axioms that are this expansion of comprehension. And one of these is alluded to as the axiom of infinity, and this is that otherwise there's simply for the finitist or ultra-finitist that there's no infinite collection of things. As a usual thinking person's approach to infinity, it has that I learned the definition of the word infinity. It means it bigger than all the numbers. So in terms of numbers, it's a number and it's infinite, and it's just always the biggest number or bigger number. Though that in terms of it being a number, arithmetic must apply, so infinity 1 is bigger than infinity. Not so in ordinal exponentiation, but 2 to the infinity and cardinal exponentiation is so established to exist and have a rule for arithmetic by uncountability. Then the second usual notion of infinity is like infinity does not exist. There are finite numbers, and they're perfectly suitable for all the things, and there are unboundedly many of them. And this is perfectly well reflected in our notion of limit and a simple forward linear inference as to why Zeno's paradoxes are ignored the other side, and we're happy with that because we can compute the limit and use it tractably in our formulas for this critical analysis of the foundations of analysis. So, set theory introduces an axiom of infinity. This posits like there exists a set that has infinitely many elements in it. We call this an inductive set because it basically satisfies containing an element for each of the infinite cases of infinite induction, where infinite induction is establishing this something so for the base case and then establishing that it is so for each following case, thus that it follows for each infinite induction. So it's called an inductive set. And it's also identified in an identification of the numbers by ordinals, the integers, the natural integers, usually starting at 0, proceeding from 1 outwards through the whole numbers, the integers. That is an inductive set, and it's called omega. That omega and infinity are synonyms in a usual sense, and different terms particular to the context in their respective settings. Omega, infinity, aleph 0 is the first aleph number, the cardinal of this set, where the cardinal of a set is the equivalence class of all the sets that can be related by a one-to-one Cartesian function. Where a Cartesian function is just a cross product in these sets of ordered pairs, that's the function in this regular set theory is all the possible, the space of the function is all the possible relations one-to-one and onto of any two sets either way, and that any particular subset of that is a function. So the other axiom then is that, well, we can't have a set contain itself because immediately and right away, Russell's paradox would apply. With the theory, the Cantor has an immediate paradox too. Cantor's paradox is, well, if you had a universal set that contained all elements and you took its power set, they would be the same and there would be a one-to-one function between them, but the power set result would be broken. So in this theory, there's instead what's called the axiom of well-foundedness or regularity. It's a form of regularity, making a rule, or well-foundedness, that each of the sets in its transitive closure, meaning taking the set of all its subsets, and all its subsets ad infinitum, contains no circular references. It does not contain itself. And so with this, basically, sitting next to infinity, we see that all the other axioms expand comprehension. It is the product of anything that they can have put together, which makes higher order elements in this theory. Whereas the axiom of, and one of these is the empty set. There exists a set with nothing in it. That's basically the first constant introduced is the empty set by axiom. Then infinity is introduced by axiom, but whereas before when we think about it, just like Russell's numbers in his paradox, he applied it to finite integers, and you said that these numbers are a number is the number it contains plus 1, that if you applied Russell's paradox to a set of plain natural integers, you would get one of these sets that contains itself, and is otherwise what caused a lot of problems for the formalization of that would be an ambiguity or lead to an incompleteness, or via extension, naively, without keeping track of these things in bookkeeping, inconsistency. So for the other axioms that expand comprehension, the axiom of well-foundedness restricts comprehension. And this isn't really something that you can say is really independent of the other axioms, but it is basically the stipulation, the non-logical axiom, where the other axioms are very natural from just combining relation in any other setting where you would have the natural predicates compose and these kinds of things. That also the axiom of infinity, besides expanding comprehension, I've introduced a second constant called omega. It's an inductive set. That it's well-founded combines that restriction of comprehension into it. So we have the axiom of the empty set, these pairing, subset, and dot union of how sets can come together in the pairwise. Doesn't really say how they are infinitely put together because, again, that leads out of the box. Then there's the axiom of infinity, which says there exists at least one infinity, and it's just a set, and all we can talk about it really is relations to it in terms of these Cartesian functions, which are also sets. Everything here is a set. That then there's this axiom of restriction says if it would break anything, it's out. Because otherwise, you can perfectly well imagine a set relating elements is this refers to itself, the thing in itself. Not necessarily this sentence is false, but this sentence is true. Or any statement or stipulation or truism, tautology, identity by itself. So all these kinds of notions of the self-reference and the transitive closure not referring to itself, and these things make it so that our Zermelo-Fraenkel set theory is well ordered. Now, there's one other axiom that came to be applied because without it, a lot of formulas were unnecessarily contrived or missing. Is the axiom of choice, or the well-ordering principle. And the well-ordering principle basically establishes this. For any given set, when you iterate over it, there's an enumeration of it in terms of the ordinals, that for every cardinal, there exists an ordinal as big as this. There are ordinals that are countable, and there are ordinals that are uncountable. This is that otherwise, without the existence of an ordinal, we wouldn't have numbers for what we count. In this sense, the ordinal is the number of something, and the cardinality is the count of something. And the ordinals basically reflect a state of these things, and the cardinals reflect an act of determining a state of these things. So that's one way to describe when we get in terms of that there are functions that are Cartesian, and these are for all our real functions in the complete ordered field, that besides standard theory and the Archimedean field, there's non-standard theory of numbers, and it has infinities and infinitesimals in that besides. And the non-Archimedean fields, like John Conway's surreal numbers, or other non-Archimedean fields, where John Conway was one of the greatest mathematicians of the latter part of the 20th century, and very famous for the game of his cellular automata, the game of life, automata, and also for his incredible treatise on sphere packing with N.J.A. Sloan. So, what we have arrived at is this first chapter of Hermann Weyl's on the analysis of the foundation of analysis, and I haven't read anything yet really from it, but that is to read off his section where he talks about his chapter 1 is split into two sections. Logical section is property, relation, existence. Section 2, the principles of the combination of judgments, and that deserves reading. And then logical inference and axiomatic method. And mathematical section reads sets, the natural numbers, and Richard's antinomy. Antinomy is another name for paradox. And we'll read about Richard in a moment. Iteration of the mathematical process. Iteration is as of induction. The circulus vitiosus of analysis. Principles of substitution and iteration. And definitive formulation of the foundations, introduction of ideal elements. Then his second chapter is called The Concept of Number and the Continuum, and its sections are natural numbers and cardinalities, fractions and rational numbers, real numbers, sequences, convergence principle, limits, the property of being Cauchy, continuous functions, the intuitive and the mathematical continuum, magnitudes and their measures, refer to measure 1.0 and least upper bound as following, and curves and surfaces, geometric setting. So turning to page 24, where there's some mention of Richard's antinomy. he does mention something like a single basic relation whose meaning is immediately exhibited underlies this category, namely the relation successor of x to y, which holds between two natural numbers x, y, when y is the immediate successor of x. It's x plus 1. Next. Current and next. The sequence, with regards to Richard's antinomy, the sequence of natural numbers is crucial to Cantor's concept of denumerability, which means countability, which, as is well known, has given rise to Richard's antinomy. The standard version of this antinomy is as follows. The possible combinations of finitely many letters form a denumerable set. This is that each sequence is constructible and yet together they're uncountable, which seems at odds because you can seed it and run them out. It's just that they never run out. The possible combinations of finitely many letters form a denumerable set. So since each definite real number can be defined by finitely many words, there are only denumerably many real numbers. And this is, if this is Richard's antinomy, we basically attribute this to Hausdorff, and then we will talk about Skolem and Leeuwenheim and Skolem. And so that Richard's antinomy is that all this is yet still constructible. And then when we get into the ordinals and the countable and the constructible ordinals, we'll get up to omega, and omega 1 being the first uncountable ordinal, and omega 1 Church-Kleene being the first ordinal, which is quite so large as omega 1 ck. That this gets into all this transfinite hierarchy and the cumulative hierarchy, and as with regards to yet at the same time, there's established this inequality, this hierarchy, and that it's transitive among any different sets, that they're either in the same equivalence class or not, according to the function theory of Cartesian functions, that the course of passage of the ordinals is in accordance with the Weyl ordering principle, and as follows from the existence of an inductive set and transfinite induction, which is the establishment of a base case for 0 and then integers, and they're each for each following limit ordinal and their integers, where a limit ordinal is an ordinal that has no predecessor, that an element of the integers has a successor, and that besides 0 and other limit ordinals, they also have predecessors. It's a reflexive relation. Similarly, it has how we talk about the element being the relation, or contains being the relation, and sets they're kind of the same thing, but one points to being a member and the other points to a collection of members. Okay. That this Richard's antinomy is a thing, and it causes a lot of people great consternation and lots of thinking about it. And so when I got to thinking about it, and let's see here, getting up into the time, there's basically a notion of how these ordinals are ubiquitous, and that when we can talk about a power set result that results that the missing element that establishes for any otherwise Cartesian function that there's something missing, and thus it's not a one-to-one and onto function, is the empty set, and so there's nothing to miss. That then there's also, with regards to counting versus numbering, that we have what's called ordering theory, which fits well with the Weyl ordering principle, the principle of choice, that there exists a choice function which will always produce a next element of a set, which is critical for most usual simple means of quantifying over a set and defining things that apply to them in our predicate calculus according to our usual quantifiers and variables of calculi, of logical inference. There's the idea that besides Cartesian functions, that this was the assumption that is always present, that it was always free, but that there exist non-real functions, maybe that's not so. So that is a brief history of the Continuum, a critical examination of the foundation of analysis, and a brief synopsis of its contents, and reflects some of the areas of research with regards to what we basically call the ancient Greeks, the continental Germans, and then the turn of the 20th century, or fin de siècle, and then that we get into how today we have Zermelo-Fraenkel set theory, and all descriptive set theory results pretty much that all of standard mathematics is written today. This is the foundation. This is the foundation we have. And so the ideas of Aristotle's continuum, which is basically infinitesimals between 0 and 1 and infinity of them, has that we would have to take apart and deconstruct some of the notions otherwise of arithmetic, so that the closures of this result that it works out the same, that these assumptions are made separate, and so that they are independent and can come together and make this thing as well. And similarly with this kind of idea of a Nyquist-Shannon continuum, or along the lines of a guy named Harvey Friedman's, the rationals are huge. This is that the rationals are countable, denumerable, the set, but still huge. Is that then that this grain is to be smooth is as a per signal analysis, and it's just an analog to the analog, quite directly. That this is where mathematics sits today, and the contents of this book make for great reading, and they're very well stipulated and at a high level, and help to explore all the concepts of Zeno and the principles, what result we have a mathematics that includes continuous uniform motion in time. And that's standard. All right then, good afternoon, and till another day.